glad to have Ben Berger with us today. He is a researcher at Offchain Labs, the lab behind Arbitrum. And he's going to do a deep dive into BoLD. And he promised to give us the perspective of the people who actually implement things.
Okay, so hi everyone. Very nice to be here, and thank you for inviting me. Yeah, so this is a joint work with all the people here on the screen. All of them are colleagues. Some of them are former colleagues at Offchain Labs. And yeah, so today I'm going to talk about BoLD. Okay, thank you. Yeah, so I'm going to start with a quick introduction to layer 2 blockchains and how the proving, and then we'll concentrate on the rightmost rectangle here, which is the proving mechanism. So what you see on the screen is like, I'd say, a pretty typical layer 2 design of a layer 2 blockchain that sits on top of Ethereum. And at least Arbitrum is built with these 4 different components that work together. The first component is the sequencer, or the sequencing part, whose job is just to receive transactions and decide on some order of those transactions. After that order has been decided, the transactions are forwarded to the execution engine, which computes the resulting state from those transactions, the state of the layer 2 blockchain. And in addition, the transactions are sent to the data management component, which posts these transactions to Ethereum. And once those are on Ethereum, that's the source of truth as to what the transactions that appeared on the layer 2 are. And the final component is the proving, whose job is to prove the result of the execution engine to Ethereum without Ethereum doing the execution by itself. And so this design allows us to scale Ethereum by sort of offloading the expensive computation off-chain and just using Ethereum to verify that the computation proceeded correctly. And so this picture, I think, is helpful to have in mind for this talk, at least. So abstractly, you can think of these transactions as being in order from, let's say, the right is the earlier one to the later one on the left. And these orange rectangles in the bottom are sort of the intermediate states, which are the result of the computation of these transactions. And at some regular cadence, the current state will be proven onto Ethereum. So on Arbitrum, for example, the distance between each 2 orange rectangles is about 1 hour. So once per hour, a state is proven on Ethereum. And of course, the main challenge of such a system is how to convince Ethereum that it proceeded correctly without Ethereum executing by itself. And ideally, we would like this process to be, we want this to be doable in a permissionless way, meaning that everyone who wants to participate in this proving should be able to do it. And there are 2 approaches to how to do this. There is the ZK rollup approach, which we will not talk about, and there's the optimistic rollup, which Arbitrum falls into. And the way that optimistic rollups do it is via what's called a dispute resolution protocol. Sometimes it's called a fraud proof or a fault proof system, which is basically an interactive protocol to determine which competing claim is correct among a set of competing claims. And the idea is that if one claim is posted, then if enough time passes, then it will just get confirmed. Again, if no other claim was posted after some window. Okay, so just to get to sort of build a language that we will talk in this talk, let us assume that the last confirmed state on the L1 is called S0, and now the goal of the dispute resolution protocol is to confirm the checkpoint state obtained from this state S0 after executing the next n steps. And the execution is deterministic. So assuming that we already know what transactions are there, and we are assuming that they are correct, the Sn is completely deterministic from S0. Okay. So right now what I want to do is go over the Arbitrum Classic protocol, which was the protocol that was up to March of this year, was the one that was on Arbitrum. And so the idea is that anyone that wants to participate can claim some assertion. And in order to participate, you need to put a stake, which is some amount of money that will get slashed from you if you lose the competition. And so as an example here, we see that we have 4 participants. We have Honest Alice and Evil Bob, both of them staked on the correct assertion. Note that Bob is also on the correct assertion. Then we have Evil Charlie and Evil Diana, the last, both of which staked on an incorrect, a different incorrect claim. And so once some deadline has passed, then there's some way to sort of do an elimination tournament between these assertions. There are sub-games, 1 versus 1. Each time someone loses, the winner sort of advances to the next level until at some point the winner gets confirmed. So here we see that Evil Bob, even though he staked on the correct assertion, he still managed to lose the first match against Charlie, but Alice ended up winning the entire thing. Okay, so this is like the meta structure of how this works in Arbitrum Classic. And what I'd like to do next is go over how each one of these matches is conducted. So let's look at the match between Alice and I think it was Evil Diana. So at the beginning, Alice staked on Sn, Diana staked on Sn double prime. And so what will happen now is that Alice, she's expected to give the first move, which is to say what is her claim on the mid state between the 2 states. Now it's Diana's turn, and now she needs to say what the mid state is. There are 2 options. Either she says that she agrees with Alice, or she doesn't agree with Alice. Let's assume in this example that she agreed with Alice. I want to say, sorry, that notice that in the beginning, they both disagree on the end state, but agree on the initial state. Yeah.
So just a question, if this is an interactive sort of argument, why can't Diana just always copy what Alice says? Or that comes in?
She can copy. Sorry, let me take one step back and say that all of these moves are governed, that there's a set of smart contracts on Ethereum, which sort of govern this tournament. So when I say that Alice submits a move, that means she actually submits a transaction to Ethereum using a wallet, for example, or to submit this transaction. And all the rules for inclusion of these transactions, like any other transaction with Ethereum, will happen. So, and also let me say, maybe it's more to your question, the goal of the adversary here, or all adversaries, is to get a wrong state confirmed. Okay, like because this wrong state may say something like Ben has decided to withdraw a bunch of ETH from his account on Arbitrum back to Ethereum, and since Arbitrum secures billions of dollars, then if a wrong state gets confirmed, this could mean billions of dollars lost for honest people. Okay, and so Diana here wants to get Sn prime confirmed, which is the wrong state. And so in this step, Diana said she agrees with Alice. And so what happens now? Note that the same invariant that we had at the beginning is sort of maintained, but on half the dispute, right? There is still agreement on the mid state now, which is now the initial state for the next step, but disagreement on the last on the end state. And so after log n such exchanges, there will be a dispute about the immediate next step after the initial state. At which point the smart contract itself will execute that operation, because the smart contract has sort of a copy of the state transition function in its stomach, and so it will just execute the state transition function and see whether, like, which of the parties is correct or not. Okay, and that way we decide. Now, this game, each player gets a chess clock, which is like a clock that is initialized to some high number and sort of ticks down every time that it's their turn to move. Initialized to this initialization time is what we call the challenge period, and if this clock is over, then that player is immediately disqualified. That makes sense? Okay. So from this story I told you, two things should be evident. One is that the honest party can force victory here. There's no way to beat the honest party, but this is assuming that the challenge period is long enough to allow sufficient time for calculating the transactions, submitting them, and having them processed and included on the canonical Ethereum blockchain. And this is considering that the adversary might try to censor or delay the inclusion of those transactions. And so in practice, today the challenge period is set to about 1 week for reasons that I don't want to go into right now. And another thing that should be evident is that the malicious party can stake on the correct initial assertion but still lose the subgame by, for example, stating the correct state at the beginning, but then lying when you post the mid state. Okay? And so what are the properties of this protocol? First, it's safe and it's live, meaning that if there is an honest validator, no false assertion will be confirmed and the correct assertion will be confirmed. Again, this is assuming that the challenge period is large enough. And there are good incentives. If there's an honest validator, there is no incentive for the adversary to stake because they will certainly lose it. Okay, what are the problems here? First, all the honest validators. So imagine that there is a group of honest validators which are disconnected from each other, and all of them want the correct state to be confirmed. But they do not trust each other. They do not know who they are. And so every one of them must participate because an honest validator, if he sees that Bob there staked on the correct assertion, he can't be certain that Bob will win, right? So if you're an honest assertion, you must validator, you must participate and put a stake accordingly. And so and because of this, the honest part, I'm jumping to the third bullet here. The total cost of all the honest parties could be proportional to the number of honest parties. For example, if there is just one bad validator, and so their expenses will not be reimbursable. And by expenses, I'm not talking just about the stake, but also the expenses of doing the protocol, which every such move costs gas on Ethereum. I'm sorry?
Drop out? Can an honest party that sees some other honest party publicly winning already and drop out?
No, but if he trusts that the other party is okay, he will not come in the first place. He will just not put a stake in the first place.
But like, so they see they see the transcript that this other honest party is posting before they decide whether to participate in the tournament?
Yeah, but I mean, they can, the way I describe this, the honest party can lie in any step along the way, right? Okay. And another thing, a problem here is that delay attacks are possible. So I didn't say exactly how the games are orchestrated, like in what order they are, but in the way, in some reasonable way to orchestrate the order of the matches in the tournament, you can show that if an adversary is willing to sacrifice n stakes, then they can delay the confirmation time of the protocol by a factor of n. The confirmation time is basically the time when the single winner is identified.
Another question. When you say the challenge period is a week,
That's the time on the chess clock.
right? So for each move,
No, so it's initialized to a week. Once it's your turn, it begins ticking down until you do your move, then it stops. Then it's the other player's turn, ticking down. So you have a 1 week in total to do your moves.
so no matter what, at the end of the week, some stake is going to be fine.
No, because the games are in order, right? So, I mean, this match doesn't start until these matches are over. for example.
So that's what you meant by multiply.
I mean, this game can take 2 weeks because each player has 1 week on their chess clock. But then this game will not be played until this game is over. Okay, that makes sense? Now you can imagine that the tournament doesn't have to be binary tree, so it's not going to be log the number of participants times 2 weeks, but it can be the number of participants times 2 weeks if the adversary is smart. But I don't want to get into that because we don't have time. Okay, so that's the classic protocol. And these are the problems. Delay attacks, and that the honest party, since all of them have to participate, it might cost a lot of money for all of them together. Like the total honest cost is too much. Yes.
Does this mean that, let's say, all but one of the honest parties will like lose a round in the tournament if they lose their money?
Yeah.
Oh, okay.
Yeah. If you lose a single match, you lose all of your stake.
So, but will two honest parties ever play a match against each other?
No, I mean, no, it's only going to be between two parties that represent a different SN. You won't have an SN against SN match. Okay. There's a lot to talk about, like what can be done here, but just believe me that adversary can delay confirmation by a factor of 1. Okay.
What happens if everyone drops out?
I'm sorry.
If everyone drop out for whatever reason?
What do you mean?
Like in all tournaments, everyone drop out, like stop, I don't know, playing the game. Like which state would be concerned then?
So I mean, these are like edge cases. All edge cases are, but for example, in this stage, if both of them drop out at this stage, then Diana will lose because her clock will run out.
It's ordered between them.
There's some way to decide whose move is first. That's like going into the nuances of the. Okay. We can talk 2 hours about this protocol, and it's very interesting. But I want to highlight that these are the main problems that BoLD addresses: the delay attack and the trustless problem. I can't trust. I'm an honest party. Aviv is an honest party. I don't know that he's an honest party. I can't trust. This brings us to BoLD, which is much more complicated, and it was deployed in March of this year. Oh, sorry, just maybe one last thing to say. Because of these problems, the Arbitrum Classic protocol was permissioned. So meaning that there was only a whitelisted list of trustworthy participants with big reputation who could participate. Okay. And BoLD makes today BoLD is permissionless. Everyone can participate. So the main ideas, BoLD still implements a bisection style game like before, but I guess the most important difference is what I call honesty commitment. Instead of committing to single states, the commitment is to the entire state sequence. And so I'm going to go into this later in more detail, but I hope you can imagine already that once anyone committed to the sequence S1, S2 until Sn, no one will, the mechanics will be such that you cannot bisect to a different state than the true Sn over 2. Because the move will verify that something is wrong with the commitment scheme. Yes?
The hiding commitment? Does it have to be a hiding commitment?
No.
Okay.
It's not like there's no issue of privacy here.
And does it have to be a non-hiding commitment for sure? Like, because if you're saying they can cooperate trustlessly,
So I'm assuming that okay, that's a good question. I'm assuming that the honest validators, each of them is actually able to run the state transition function by itself and hash or do the commitment themselves.
Okay, so it's a hash and not a commitment technically, right? Because I mean it is a
It
commitment.
uses it's gonna be okay. It's gonna be a in the end. It's gonna be a Merkle tree of the state sequence.
But it has to be deterministic, right? Like
Yeah.
it can't be non-deterministic, like
Yeah. There's so they decide like okay. the hash function, the smart contract knows what the hash function is.
Sorry.
No, but those are good questions. The honest parties, all of them know what hash function to use, how to do the commitment. It's all like,
And then what
Agreed.
commitment to expect, they also know?
yeah, if we both are honest parties and I do the commitment to the correct state sequence, then Aviv, who is also honest in my story, will know this. You want me
In
to
real
know
life?
this? Okay. Okay, so because of this property, BoLD allows only one stake per assertion, as opposed to what I told you before, where Alice and Bob, honest Alice and evil Bob, both stake on the correct assertion. And as opposed to having multiple 1 versus 1 games like before, now we will have an all versus all type of game, which will require like a novel timer system and careful move design and graph that sort of represents what's going on in the protocol. And my hope for the rest of the talk is to explain at a fairly deep level how this works. Okay, and at least the naive version, which is the single level version. The currently deployed protocol is a multi-level version, which I will talk about a bit in the end. But you can't understand multi-level without understanding single level. So we'll start with that. So first, I assume that n, so the length of the sequence, it's always, also in practice, it's a power of 2. It's gonna always. And again, the goal is to confirm the last state Sn, which is, again, I emphasize, it's deterministic from S0 after executing n steps of the state transition function. The protocol will maintain an initially empty protocol graph G, which is going to be a DAG, so a directed graph without cycles. The protocol will proceed in rounds, and in each round, the participants can submit protocol moves, which, I mean, they will see the state of the graph before and then submit in each round. And these protocol moves will essentially modify this graph. Each node represents some claim about subsequences of the big state sequence. And an edge A to B in this graph means that B is a refinement of claim A. So you can think of B as being the bisected claim of what A used to be, which is made as a response to some counterclaim A prime. A prime is a counterclaim to A. Roots in this graph represent the main assertions. For example, one root could be, so the honest root would be, assuming S0, the length n sequence following S0 is S1, S2, Sn. So this is the honest sequence. Okay. So the node structure is pretty straightforward. There will be it's essentially, there's more stuff in practice, but importantly, it's essentially a triplet, which is the prefix, which is a commitment to a sequence, to some prefix of the entire sequence, S0 say to some SP. Suffix is a commitment to the sequence. Presumably, it's a commitment to the sequence of length immediately following that. So from SP plus 1 to SP plus sub length, and it's always going to be a power of 2, the sub length, and it will represent the claim, assuming we agree on pref. Then sub is the correct state subsequence of this length following pref. And I might sometimes use this notation too to represent this node. Okay. Okay. So, as I said, commitments are Merkle roots, so made using some agreed upon hash function H. And new nodes, as I said, are added by protocol moves. And once a node is added, it's never removed from the graph. Okay, now an important concept or definition of rivaling nodes. So two nodes A and A prime are called rivals if they agree on the prefix, agree on the length, but disagree on the suffix of that link. That means that they are competing claims. Okay. Now about timers. So for each node, the protocol maintains two types of timers. There's the local timer, lambda v, which is initialized to 0 when the node is created. And it increments by 1 in every round. So you can think of a round here as a block, an L1 block. So every block, it ticks by 1 until it becomes rivaled. At that point, it doesn't tick anymore. And note that this is already a difference between this and what I told you before. Before the clocks were sort of counting down, and here they are counting up. Okay, and this represents the amount of time that this claim hasn't been challenged yet. Okay, and there's also the bottom-up timer of a node, VV, which aggregates the local timers along some minimal complete path starting at this node. So complete path means a path that cannot be continued. And so basically, just to say what this means, it means that for every number t, this bottom-up timer of v will be at least t. If for every complete path starting at this node, the sum of the local timers is at least t. Okay? And already a spoiler, I will say that the honest party's goal here will be to maximize the bottom-up timer of the honest root. You can think of each honest path in this tree as corresponding to some 1 versus 1 game from the previous story I told. And the amount of time accumulated over that path is sort of how much time this one side has sort of justified that it should be the winner. Stop me if there are any questions.
So in the root node, the suffix is all the components, or the previous the suffix, right?
Yeah, I'm going to get to that, but
Sure.
yeah, the roots will be in principle the prefix will be just S0, and the suffix will be presumably a commitment to the entire state sequence. So now I'm going to talk about what are the legal moves in this game. So the first is the create root, which gets presumably a commitment to the sequence. And what it will do, it will just add the node, this node, which is the commitment to S0, which is a smart contract. That's like a constant inside the smart contract. And then it will add the commitment that the user provided and the length n. Now, just to keep in mind that the smart contract, he doesn't check or he doesn't know what this commitment means. He just posts the commitment. Okay, but if the honest party is done right, then he sends the correct commitment. It can be garbage too. And the root creator must place a stake, which again is to be slashed if that root does not win. And I will say what winning means. Okay. The next move is bisect, which the arguments that the user provides is the node that he wants to bisect, and saf-pre and saf-saf, which are presumably respectively the first half of the suffix commitment and the second half of the suffix commitment, which are both commitments by themselves. Okay, so what the node will do is first verify that the node is rivaled. No node can be bisected if it's not rivaled. It will check that L is larger than 1, so you only bisect suffixes which are presumably at least 2 sequence states. And it will verify that the suffix, which already exists in the graph, so it will check that V exists in the graph. It will check that the hash function, basically that saf-pre and saf-saf are consistent with the commitment that existed in the graph. Okay, this third bullet makes sense? Okay. If all of these checks pass, then the smart contract will create, so this node already existed, and it will create these two children and the two edges. Unless the left child already existed also before, which we will see later that this could also happen. Okay, but if it didn't exist, but if this child already existed, then the smart contract will just add the edge. So, but we will see. I don't think about this point for now. Okay, now importantly, what nodes are added, which I didn't say. So here, the left child is just saying, well, we agree on the same prefix, but now the disagreement is on the half of the suffix. And what is the right child? It says, well, here in this claim, let us assume that we agree on all the way to the first half. And assuming we agree on this, now we might disagree on the second half. Okay, and note that the length of the suffix in question sort of decreased by a factor of 2. Any questions about this? Okay.
Just to make sure I understand. So what happens is somebody else submits a node in some sense, or submits a different set of commitments, and then the idea is the smart contract is going to create these two nodes.
Yeah. The user submits a transaction to the smart contract to the method bisect,
Right.
And he gives the arguments, the node which presumably already exists in the graph,
Right.
and these two commitments.
Right.
And yes, sorry.
No, and then depending on that, we create two new nodes, which might either be different than the second half, or wait, what was the?
Let's assume that that suffix is really the commitment to the correct sequence, S1 to Sn. In this case, in order for these checks to pass, if these checks passed, then assuming that age, the hash function is collision resistant, again, assuming that age is collision resistant and that Suf is really the commitment to the honest sequence, and that these checks passed, it must mean that this Suf pre is the commitment to the left half, and this is the commitment to the right half. So this shows you that if Evil Bob here started with the correct sequence, and he tries to bisect to this way such that the node, the state in the middle is something else, then this check will not pass.
Right.
So Evil Bob cannot bisect to halves that don't agree with what already existed before. I'm willing, like this is like a fusion point.
Is this like a meta tree? Like there's a Merkle tree, and now is this like a meta tree off the Merkle tree? Like, are you building a hash chain of all of the previous transactions, or are you showing like this is what they hashed to in the Merkle tree?
So this drawing here is part of the protocol graph. Doesn't have to do with the Merkle tree. Each of these Suf, Pref, all of these are cryptographic commitments, which are roots of Merkle trees.
Okay, and then
That
roots
makes
of
sense.
subtrees as well when you do bisect.
Yeah. Essentially, if this Suf is it's the root of some Merkle tree, then and these checks pass, then it must mean that Pref that Suf
children.
3 and Suf are the roots of the immediate children. Okay. Any other questions?
Sorry, for the V's rival condition, I remember you mentioned the rival definition. Basically, it means that there's some other V at the same level as.
Yes, exactly.
Because they have to share the same prefix, right?
They have to share the same prefix. They're in the same height,
Same height.
but they disagree It says, it's another note that says, I'm assuming that pref is correct. I'm just disagreeing on the suffix. Okay. Okay, this is like a slide that tries to explain all of what I said before, but I now realize that it's too much notation. But never mind. I think that this is better. I'm just going to skip this slide. This is just explain like it in a more like granularity level what is going on here. Okay, the final move that I want to present is the one-step proof, which I mean, in the end, you get to the step where you disagree just on one state. So this is what resolves this. And what it will accept is some node V, which presumably exists in the graph, and some proof pi, which I'll talk about in a second. It's going to verify that V is rivaled, like before. It's going to verify that L equals 0, so meaning that this is basically that this is a node that has a claim on a single state. And so assuming that V is this node, what it will verify is that when you run this transition function on the end state of the prefix, you get the SP plus 1, which is represented by the self. Okay, this is what it's going to do. Now, how does it do it in principle? Now, remember that each of these states. So the state, when I say state, think that this is like all the account balances. Like it doesn't all fit. So the states themselves are also commitments. So, for example, what does the proof pi that is given as input contain? First, it needs to contain the rightmost Merkle path. So remember, this is the root of a Merkle tree. It will contain the rightmost Merkle path to sort of isolate SP, to get the commitment just to SP. Now, after you've done that, and you have the commitment to SP, and you have supposedly the commitment to SP plus 1, there is some very, 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 very clever engineering how to be able, in the small resources that the smart contract lets you, to sort of do the computation from SP to SP plus 1. The proof will contain hashes to part of the state that don't matter. You can think that the move from SP to SP plus 1 is just maybe to add a number to some register in the state. And so the proof will sort of give all the correct information to be able to allow the smart contract to execute this. But I don't want to say any more about this. The point is that the rightmost Merkle path allows the smart contract to get the supposed commitment to SP, the supposed commitment to SP plus 1, and then it's just able to verify whether when you do the state transition function from the SP, you will get SP plus 1. That's like a topic for a 3-hour lecture on how that thing works, which will not be done by me. Okay, so any questions about this?
So one, maybe a stupid question this related to that. So why do we need these validators at all? Like, why can't I have a smart contract that just computes the state and keeps posting? Like, why can't I just run that smart contract, which was, I guess, established long ago?
Why not just run from S0, do n steps? And
Yeah, each time I want a new state, I have the smart contract.
well, the whole point, okay. I'm glad you asked this. Like, the whole point of this is exactly not to do what you said.
Okay.
I mean, we don't want the smart contract to execute all these n steps because it's very expensive.
Right.
But this is done on Ethereum.
Right, but you just said there is a very efficient way to go from SP to SP plus 1.
But that's just one
okay.
state.
You don't want it to do it n times.
Yeah, exactly. This method, I mean, flying up and get a bird's eye view of this. Like all of this is going to essentially happen in log n steps, essentially, in order to resolve this. So where n is the length of the sequence. So the whole point of this entire story is exactly not have Ethereum compute the states by itself. This is why layer 2 exists.
I have a similar question. So, suppose you have to do this, like bisection, like dispute protocol, because someone, like there's at least two people that claim differently. Then everything that I suppose you're going to describe the efficiency or like how resource intensive this is, but is the entire bisection protocol still like more efficient than computing for that single time everything from S0 up to Sn, like from gas wise?
Yes, it will still be. I mean, it depends how much funds the adversary is willing to spend. Because if the adversary now invents 1 trillion different stakes, then it will make the honest party have to do more bisections. But this will cost so much money that it's not going to be feasible. And that's part of the, like, I'm going to talk a bit about how we decide what the stake size should be. But this relates in part to what you just said. But again, this whole thing is made with incentives in mind. So because I am hoping to convince you that the honest party will always win here, always. Like if there is a single honest validator, it will win. Then this will never happen. This game, no one will. The stakes are very, very large. So today's stakes are like 3,000 ETH, which is like $10 million or something. So this will not happen. In practice, what happens? The honest party, which is Offchain Labs, submits their honest root, does the create root with the honest move once every hour. No one challenges, and it's just confirmed after some time.
Is there a reward for confirming these states, or is it only incentive?
There is some design of prover markets and how to incentivize people to do this, but I don't want to talk about this in this talk.
Wait, so if Offchain Labs is dishonest, nobody will still dispute it anyway, right? Because
Why?
it's too expensive.
What's too expensive?
So you said you have to have 3,000 ETH staked to even make a dispute?
Yeah, well, I don't, one sentence, and then I don't want to continue talking about this because this is like a much larger topic, but this Arbitrum 1 secures around $20 billion today. So in order to save $20 billion, someone will come up with $10 million. That's like one assumption. And I think that's enough to deter people from, okay? But we can talk about this offline too. Okay, if the proof is successful, it creates a special node V proof, which is essentially the same V, but just says that it's proven. And the local timer of this node is initialized to 1,000, to infinity. Basically, and so this path that led to this, now we don't have to take care of it anymore for the bottom-up timer to be large enough. Okay. So finally, how does someone win this game? Well, a root is what we call confirmable if its bottom-up timer surpasses some threshold, which is predetermined. And the first root that becomes confirmable is declared winner. And of course, the question is how to set the threshold. And the answer is that we need to set the threshold so that the honest party will be guaranteed to win with some strategy, assuming some attack model that we want to defend against. Okay, so I want to say what the honest strategy is, and then I'll talk about the attack model. So the honest strategy is really the most straightforward thing. The first thing you will think about if you think about this for some time, which is at the beginning, just create the honest root. And then in every subsequent round, basically defend every node that is a descendant of the honest root in the tree. So presumably, if a node is a descendant of the honest root, it means that there were it means that the honest party before already bisected until until this node was created. And so if one of these nodes is rivaled, then you do a corresponding bisect, or if it's in the lowest level, you do the one-step proof. So again, you first create the honest root, and then you bisect or one-step proof according to your needs, to what happens. Make sense?
And parties know the honest root because they can compute the honest root.
Yeah, the honest validators, they are
They know.
computing, they know everything, they're following the chain. Yeah. Okay. Now, what is the attack model? Or what are we fighting against formally? So we assume that at the beginning of every round T, moves are submitted to the protocol, and these moves may depend. So the honest party, the moves that it chooses to submit may depend on what happened in the past. So we seize at the beginning of the round, the honest party sees the state of the protocol graph, and there are some honest moves and some adversarial moves that are submitted. We are assuming that the adversarial moves are just executed immediately in the round that they were submitted. So again, these rounds are Ethereum blocks. So in order to be executed, this means that they need to be included in that block. We are assuming also that the honest moves have some nominal delay, which is like the regular time that you may expect for them to be included. So think of this as the time to realize what move you need to do, to prepare, to compute all the hashes you need, and submit it. In Arbitrum, we wait. So if we had needed to compute it to submit it at round T, we will wait until that block is finalized on Ethereum before submitting, because we don't want reorgs and things like that. This all goes into the nominal delay. And so what this means in the formal model is that if a move is submitted by the honest party at what would be submitted by the honest strategy at round T, then the default deadline for its inclusion, for its execution, is T plus delta, where delta is some parameter. In practice, it's like 20 minutes today. In addition, the adversary has a censorship budget, Cmax, which we assume that we know. This is like 1 week. We assume that the adversary today cannot censor more than 1 week. And so the way the adversary uses this is, if it decides, it can decide at any round to spend one censorship unit out of this budget. And if this happens, then all honest moves that are pending at that time, that were submitted but not executed yet, their effective deadline increments by 1. Okay? Okay. I have a very thorough execution example, which I would have liked to go into, but I don't think I have time. Maybe I'll go into after I talk about some more stuff. So what we prove in the paper is that if we set the confirmation threshold to be at least Cmax, which is the censorship budget, plus 1 plus delta times log n over 2, and I'll give intuition what those numbers are, then the honest root will be declared winner. And when will that happen? At most, at round threshold plus, basically plus this times 2. And so the smallest number, if you set the threshold, the smallest threshold you can set is exactly this right-hand side. And if you set the threshold to be that, then you will win by round twice that much. And so in particular, this number is estimated to be 1 week, 1 week plus nominal, 1 week, basically. Then what this theorem tells you is that the honest party will be confirmed maximum 2 weeks after the protocol started. Yeah.
And this is in contrast to like the 2 times the log number of games we have.
Yeah. Yeah. And And it's not, the adversary can be smarter and make it not times log n, but 2 times n, if he's smart. Okay, this log n over 2, this is the maximum amount of moves along some path. So log n is the number of bisections. There's one for the create root and another one for the one-step proof. Okay. So, and what do we get from this? So the good properties we had before are still maintained. If there is we have safety, liveness, and good incentives. But now the cons from the previous protocol are now completely eliminated. We need just one honest stake, because again, if I see that honest Aviv has bisected correctly up till now, I can just continue to watch. I might need to step in and provide more moves to sort of advance the path if he goes to sleep or something. But we don't have this phenomenon of having to start from the beginning. And the honest party's total cost is in gas and in stake is proportional to the number of malicious stakes. So the malicious stakes is this, equivalent to the malicious roots. And so what this means is that in the end of this, in the aftermath, the total honest cost, like the expenses that the honest parties together spent on this, can be in principle reimbursable from the slashed stakes, if the stakes are large enough.
Like linear? What's proportional?
Yeah.
Hypothetically, you could also do a bisection between the stakes, right? Let them sort it out.
So small n is a constant. Yeah, so basically, the number of taps you need to scale as the number of malicious stakes, and each path is constant amount of expenses you might need. Log n is a constant here. So, but I'm going to talk about this in a second. Like, I don't know if I think we're at time, but if like I have 3 more slides about multi-level BoLD and resource exhaustion, but then okay, I'm just going to say one thing about multi-level BoLD, which is the actual version. So that's deployed. So in practice today, this n is around 2 to the 69. In like we said that Arbitrum submits once per hour. 1 hour of Arbitrum computation can be at most, if the adversary is smart enough, can be at most 2 to the 69 ops, like opcodes in the computer. But of course, to create the root, we need to do a Merkle tree of all the states in between, which is completely infeasible. So what to do? Instead of running BoLD on, like I showed you, what we do is we run BoLD on not the state sequence from the state, not the sequences the S1 to Sn that are that we get them from invoking the state transition function once. Instead, we run BoLD on what we get from the iterated state transition function, which runs basically the state transition function composed with itself. So instead of S1, S2, S3, S4 until S8, we do S1, S4, S8, like in multiples of 4. And then what happens if we get to the one-step proof level? That means that we disagree on a chunk of states now, and which are disputed. And so what we do is we recurse and do one single level BoLD just on that step range. So for example, we can run BoLD on, like if n was 2 to the 69, we can run BoLD on n prime equal 2 to the 26, which is maybe feasible to compute a Merkle tree, where each such range is really represents 2 to the 43 small steps. And if we get to the one-step proof level, then we run one single level BoLD on that 243 disputed thing. Okay. I have 2 more slides about how we set the stakes, but I don't have time, unfortunately. So to summarize, I presented BoLD, which is the currently deployed dispute resolution protocol on Arbitrum, which satisfies safety, liveness, and good incentives, and also it's resilient to delay attacks, and it has much less costs compared to the current protocol, like in the worst case. And yeah, that's all I have to say. Thank you.
Questions?
Thank you for the talk. I was wondering, so in the original version, let's assume there's only one honest party. I understand that there was the issue that you might need to have multiple honest parties that need to be alive. But like if you have one in one game in the tournament, like basically you're bisecting the like sequence of states, and you always choose one of the two sides to go to, and you have to defend like one of the two sides. So you have to do something like log n steps. In the game that you're proposing, an honest party, again, assume only one person might need to defend the entire tree, potentially.
Yeah,
So it's not now, like he might need to do like actually n like defenses, like n bisect the
where n is the
number of transactions, number of
malicious of adversaries.
so like if he bisects like a single node, you would think that you don't have to defend later on potentially one of the two sides. But if you have multiple like adversarial original roots, wouldn't it be possible that you would have to defend all of his
Yeah, so
children?
that's a very good question. And this would have been evident if I had showed if I had shown you the execution example, which I didn't have time, then that would have made evident the answer. But basically, for any given, okay, there's the honest root, right? Then there's say there's just one adversarial root, right? If there's just one, you can show that there's only one bisection path that you will need to defend at each time.
Similar to
So basically, exactly,
Yeah.
similar to that, to
single
what
game
is,
from the tournament before.
exactly,
Okay.
it's very similar.
But
Basically, you will bisect and you will create two children, but one of them you will not need to touch as much.
exactly. But if you have multiple adversarial,
Yeah, so the number of parallel bisections that you need to do, like on the same height, is might be exactly the number of roots equals to the number of roots. So put it another way, the amount of work the honest party needs to do is proportional to log to the height of a path times the number of roots.
so in the worst case, it could be everything.
Yeah, but
But that's too expensive for the adversary.
yes, I mean the adversary, for it to be everything. So when n equal 2 to the 69, the adversary will need to do 2 to the basically 2 to the 69 number of steps.
Are optimistic rollups the way to go right now in Ethereum? Like, is that the most popular, or was it the other one you mentioned was like the ZK rollups?
Yeah. Yeah, so in terms of like how much usage there is today, like how much money is secured
Yes.
by the protocols, then yeah, like the optimistic rollups are the by far the leading.
I see.
But of course, there's a real problem of, once you post the assertion, it takes a week until it's confirmed. So it takes a week until it's confirmed, and that's a problem. And with the ZK, so a ZK rollup, basically you post the state and you post a validity proof together, which is verified by a smart contract. But if that works, then that's the end goal, because it's confirmed immediately.
There's no week long.
But this is much easier to implement because, I mean, ZK proofs are much harder technologically to do. And they're also very expensive to produce. Here, you just need to do a hash function of the state, which so between 1 hour and it's, if you optimize, if you do the hashing clever enough, then you don't have to do it all over again, because many parts of the tree will be, or many, like a lot of the time that the states will be the same, or almost the same. That's all engineering, super interesting about how to optimize that sort of stuff. But in principle, it's a much easier solution. And another problem of why ZK rollups, like Arbitrum is also working on integrating ZK proofs, like to do some hybrid protocol with the optimistic proofs. The problem is that, again, these systems secure billions and many billions of dollars. So if you think that there might, for example, in the ZK proof, if there is a soundness bug, that's a catastrophe. I mean, that's really a catastrophe. And so people should be very cautious before they trust that the system has no bugs. And so what are intermediate steps of like combining the two together, the two systems, so that we can gain confidence that there are no soundness bugs, for example? That's like a very interesting project by itself.
Let's take
Yeah.
the speaker again.
Thank you for coming.